Guys, thank you and welcome back to the continuation of this important episode in dealing with rooted access network with regards to campus network designs. Now, from the videos earlier, and thank you for subscribing and liking the videos. Leave your comments, your feedback, um, information you think will be helpful for viewers, something you think I've missed and you like to contribute, please feel free. We can make this a community project to help many. All right, so last night um, I discussed these areas. Area 1 being the data center, Area 0 being the core, collapse core, and Area 10 being the access layer. And this access layer, at the moment, I only have one switch. In the future, we may have to add one, but this is to give you heads up on how to network, for example, a building, and get the voice and VLANs and data VLANs to be able to work, get an IP addresses from an IP helper like this one here, and carrying on working. And when anything goes wrong, there will be resilience with the uplinks, so they can go this way or that way. So why don't you just sketch that for a moment? I'll bring this tool up, and I'm gonna put it here. So okay, so what I need is resilience really. So this route is supposed to go up. If there is any issue with this link, I want that route. Let me try and get a different color. I want this route to be green, to go up. So it can follow this way and come that way and get the resources it needs. Okay, so this way, and if it goes down, that way, that way, that way. Remember that OSPF is short path first. So as far as this guy is concerned, the closest path, and if you look at it carefully, it could be this way or that way. It's all 1, 2, 3, 1, 2, 3. So it's equal cost multipath. Okay. All right. Let's go ahead and clear this, and let's review what we have here. So yesterday I mentioned that you have to consider the areas based on, for example, the zones, and so that loop back and that loop back and all these subnets here all these are supposed to be in area 0. This is in area 1, and when I scroll down, and I can't at the moment, but that's going to be in area 10. Okay, so let's close that. We want the links that go to access area, which is the access layer. We want those links to be OSPF network type point to point. We don't want this area to ever behave like a backup designated router. But to explain that better to you, let's just start this, and let's start. Well, waiting for that to load up. Okay, let's start that as well. And then finally, we're going to start this access layer 3 switch. Okay, so from OSPF point of view, I'm going to go over here and I'm going to see the written table, OSPF interfaces and neighbors to see what OSPF is saying so far. There are a number of syntaxes we can use where OSPF is concerned, and I'm going to be using a number of them whilst I wait for OSPF to load. Okay. Let's let's go and do show IP proto. So definitely area 0, the 10.10.100, which is the interlink, 172.16.200, which is coming down this way, the subnet. Okay, they all participate in OSPF. So show IP OSPF interface brief. Let's remove the key. So what I see here is DR. So this subnet at 8, 6, 9. There's 9 here. .200.1 network. 200.1. 100.6. 200.9. The 200 network over there. The 200 network over there. Then we have the 100 network. When I go here and do show IP OSPF interface brief, it shows me DL, and the back. What I want to do, or what I want to see, is this core A being the main DR, as you can see here, and core B being the backup designated router, and only allow these links to be network type point to point. They should not participate in any sort of OSPF elections or try to become the DR, the BDR. These are layer 3 switches. They don't have much capacity. We don't want to burden them with a lot of requests from everywhere else. And of course, the amount of traffic these can handle, this cannot. And so if I try to make this a BDR and something happens here, all the traffic routing from wherever that way, from anywhere else, will bring this down. So we want this core A, which is a good chassis, and that as well, to be able to cope in dealing with traffic and throughput as it's been designed for to do so. So here, what we're going to do is, let's open this up. try again and do console and let that load. In the meantime, yeah. So that's its neighbor, the 13 and at 9, but DR and DR, that's okay. But we want this guy to be a common PTP link. Okay, so that's what we're going to do. And keep an eye on the core A. Want to make changes and see what it says. So the interface I'm concerned about is F0 not and F0 1. So on the A, conft interface F0/0, and I'll do IP OSPF net network type point to point. So the correct sentence is IP OSPF network point to point. Now you'll see that over here, this is saying loading done, interface 1 down, is loaded again. But on this side, when I do show IP OSPF neighbors, we will see what happens, because at the moment, what used to be the DRs have become the BDRs, and the interface, the 200.9, 209 and 10 are BDRs here. But let's see what we get when we do the other side on the core. So conft interface F0/1 IP OSPF the type is point to point. Okay. So now I'm gonna head over to so I can see I have a point-to-point link down there. and I can do all the other point-to-point where necessary. So I'm here now. Why don't I just go ahead and do that for interface F40 here. And then over here is IP OSPF network point-to-point. Alright guys, so we've done the network point-to-point. To IP OSPF. Label. And it's clear. I'm aware of these guys, 213 and the link going up. The state not completed yet, so we can wait around and see what happens. Go over here and do start. Remember, we are aiming for uplinks to be point-to-point. Except the interlink between core A and core B over F0/0, respectively. We want those to become members of the OSPF election, so we can choose who is the DR and the BDR. Now, on the data center layer 3 switch, going to ensure that we have network point-to-point for the respective interfaces. Remember, with OSPF or any other routing protocol, whatever you do for one side, you must do for the other. If there is a mismatch, depending on the routing protocol, I know at least for OSPF's sake, you would find that it will stop working. Now when I go show IP OSPF first, let's see what it says. It knows about 100 or 10, 100.6. We need to make sure those are point-to-point links. So conf t interface f not IP OSPF network. check that. F01. Show IP route, OSPF. Still knows about all the interfaces down there. I'm gonna go down here and turn this on. Duplicate. Let's see what IP address this really is. I think I made this the 10. I think it was 40. Let's find out. 10.2. Is the IP address. So now can we ping? Let's enable the server. So this PC2 is all the way down there. We want it to be able to, so it's all the way down. We want it to go across all the way and get to ping the server. So let's have a look. Ping 172.16.100.140. And there we have it. Now we're gonna have to trace the route to see how it's getting there. From our point of view, I want it to go this way, that way, this way, and that way. So it's gonna go 16.10 first, 16.200 second, 16.100 third, and then 16.128, 16.100.128. So when I do trace, let's check. So let's bring our tool across again. So the traffic leaving from this laptop goes all the way here, goes all the way there. So we have 16.10.254, which is the gateway, which sits below here. We have the 213 network. Quite interesting. It's used the other route. So let's see why is it faster. So it went this way, and then 16.100 went that way, and then 16.100 network it went that way. So let's find out, is there any interface turned off? Why is it using that route? Is that route the fastest? So it goes 1, 2, 3. How about this now? It would have done the same. 1, 2, 3. It's equal cost, so it shows whatever part I wanted to use. Okay, so that's the reason why it's done that. Okay. So let's ping that server and hang in there, guys. Let's ping that server because I know it's using this route this way. I'm gonna block this route here. but show up interface brief. Fill it up. F01, and that's up. Okay, good. F00 is up. F40 is up. Loop back is up. Okay, so that's fine. So it chose to use that route because it's faster for OSPF, or it must have been the route it got earlier. And so, but it's equal cost multipath, so it's still perfectly fine. Let us check if we can turn off this interface and keep the pings going here. So you keep an eye on the pings, please. Yeah, you keep an eye on the pings. And let's go to router 1. And router 1, how do I know if traffic is coming? So if I come through first Ethernet 01, so I do show interface first Ethernet 01. Let's have a look at what's happening there. I already can see 251 packets. 89 broadcast. 198 packets. Is there activity on here? Surely I can see activity on there. Why don't you compare with router 1 interface F00? Because I didn't use that route. It's not a lot of activity really, so but I can use Wireshark to check which route it's using, but I do know it's over here. So what I'm going to do is I'm just going to go conf to interface f0/1, and when I do shut, let's see if it's true. That's true, I was using the route, but then this recalculating will form the adjacency, and it is on a different route now. You get it? So still working perfectly fine. No shut, bring it back. These are all point to points. And the DL, on the route of the DL is pointing that way. 16.100.254. Has learned about it. /25. Alright, so let's Python things up a bit more. What if I give an IP address to this machine here? Let's give it a random one. Let's give it 21. Let's see how quickly OSPF learns about that host. and can get systems to be able to speak to it. Okay, so to set an IP address, you do IP. Let me show you. So it's IP, the IP address, and the gateway. So IP 172.16.10.21, and you said this is /24. 172.16.10.254. Let's save that, and then let's ping a point. Ping 172.16.10.254, which is the layer 3 switch, so we can get to it. So the gateway for the machine is working fine. Now that we've done that, can we ping the server 172.16.10, and we did 40, I think. Okay, let's try that. Lose 1 or 2. Okay, that's not the IP address. 100.140. Perfect. And it's already pinging. Ping 172.16.10, and I said 21. Let's see what it does. So we have end-to-end connectivity all the way from this server coming all the way to this network here. So with VLANs, what you do is you create something called IP helper. So what you would do is the VLAN these guys are part of, let's just draw it again. So normally what you would have is that VLAN this is part of, but now they're on the same VLAN anyway, so on broker's domain, but that VLAN, let's call it the data VLAN. So it's VLAN, and please forgive me because I'm just trying to write the mouse now. So let's say this is VLAN 20. What you do is you write IP helper. IP helper address. And then we write the address of the server. That's 172.16.140. And because this network can get to it, all the machines that are going to be here can get IP addresses automatically from that DHCP7 data center. And it doesn't matter if this link goes down or that link goes down, as long as one of these is up. So it's either this one is up or that one is up. It would use whichever one is available to go up. I'll use that one to go out. Okay, so here we are. So that's how it works. Um, it's very important that you only make those calls, the important designated routers and the backup designated routers. Um, Let all the access layers be omitted from the OSPF election process, and just be uh, stop areas where users can just get information back and forth without making changes to the topology too much. And so that's it with regards to networking the data center, getting devices on this end, this building here. Let's just sketch this building here. So, this is this building here, and yep. So that building here, users here can carry on talking to systems in the data center without much hassle. So thank you for viewing this. There's a lot to take in right there, but take your time and yeah, try and mimic this lab. I would make it available for you to download as well. I will give you a link to get to it. So um, you would see that in the description, or in the next upcoming video, or a video that I may call OSPF Lab. But if not, I will just put it in this video description, and then you can head to the website and grab it. So thank you, and we're gonna work on later with the stub area, passive interfaces, why we use them. But these are things you can read up really, and so I would just get information together so you can have it. But ideally, what you do is, if you don't want an area to advertise any OSPF link state changes, what have you, you can say passive. This interface, make that interface passive. So you can do under the router OSPF. You can do passive interface default, meaning that all those interfaces will be passive. They don't talk back. They don't. DS is just to work. But then if I want to get update from a particular zone, like that zone, or like a zone here, or a zone then I wanted, then I'll make sure that I'll make it non-passive. So I'll say no passive in that interface. But these links, I can make them passive if I want to, and this link I would leave it as because if a new machine comes on, I should be able to get to it. But we'll talk about that in length on another video. But take your time and go through the videos from number 1 coming down, and really you can use this tutorial to help you in production to build a rooted OSPF access network in a campus. So thank you for viewing, and we'll go over much more with troubleshooting and what have you in the next videos. Okay, thank you, and see you on the next one. Bye bye.